we shall introduce Hess's law. Some reactions, for example the rusting of iron, occur too slowly for the enthalpy changes to be measured by calorimetry. On the other hand, some reactions, such as dynamite exploding, are too rapid for their enthalpy changes to be measured by calorimetry. In 1840, Russian chemist Henry Hess formulated a law that facilitates the calculation of the enthalpy changes for such types of reactions. Carbon burns according to the equation below. If this reaction is carried out at STP conditions, the enthalpy change produced is called standard enthalpy change, and it is symbolized as shown here. For fair comparisons of enthalpy changes, it is agreed that they all be carried out under the same conditions of pressure and temperature that we call STP. So here is how carbon burns according to this equation here. Carbon is reacting with oxygen to give you carbon dioxide, and that amount of energy is produced for every mole of carbon that's burned completely in oxygen. However, if carbon is provided with only half the amount of oxygen, it burns as follows. So here we are giving carbon a full mole of oxygen, and it burned completely to give you carbon dioxide. So if the amount of oxygen supplied to the carbon is limited, as in this case, it burns to produce this dangerous gas here is called carbon monoxide. But look, only that amount of energy is produced when carbon is burnt to carbon monoxide. However, if given the rest of oxygen, carbon monoxide is burned to produce carbon dioxide according to the equation here. So that is my carbon monoxide here. If I give it the next half a mole of oxygen, see what happens? It's now burned to give you carbon dioxide. And the amount of energy produced is that. Just a point to note. So if we are burning carbon and we're limiting the amount of oxygen that it's getting, look what happens. You're only getting that amount of energy. If we combine equations 2 and 3, look what we get. So we bring down equation 2 here. So that's equation 2. We bring it down there with its energy content. And this is equation 3 here. We bring it down here along with its energy content. When you add these two equations, look what happens. You can see that carbon monoxide is common on both sides. So we remove those and we add these together. Carbon along with this half, another half here gives you 1, and you get carbon dioxide. You can see now that when you add these two equations, you get the same amount of energy than when carbon is burned fully in oxygen in this one step here. So Hess is saying that if a change takes place in a single step and it produces a certain amount of energy, as happens here, but if this very change takes place in a number of different steps, then the sum of the energy for each of those steps is equal to the energy produced when it takes place in a single step. So this reaction took place in a single step, but look, the same reaction here can take place in 2 different steps, this one here and this one here. So what you're saying is that the sum of the energy produced by these 2 steps must be equal to the energy that is produced if it takes place in a single step. So that's Hess's law. And the following enthalpy diagrams are used to illustrate Hess's law. That is carbon reacting with oxygen in a single step to give you carbon dioxide as products, and that's the standard enthalpy change there. Now this very reaction can take place in these 2 different steps. First we start with carbon reacting with only half a mole of oxygen to give you carbon monoxide, and that's the amount of energy produced here. Then the carbon monoxide is then given next half a mole of oxygen to produce carbon dioxide, and that other step here produces that amount of energy. So when you add the energy produced by these 2 steps, you can see it's equal to that. So that summarizes Hess's law. Let us see now how Hess's law can enable us to calculate the standard enthalpy change for a few reactions that cannot be calculated using calorimetry. So the one that we're looking at is carbon reacting with hydrogen to give you ethylene or ethene gas. And we want to find out the standard enthalpy change for that. You will be provided with a set of reactions whose standard enthalpy changes have already been determined by calorimetry. So in this first one here, you're given carbon reacting with oxygen to give you carbon dioxide and its standard enthalpy change. Hydrogen reacting with oxygen to give you water with its energy, and then methane burning in oxygen to give you carbon dioxide, water, along with its energy produced. So this is the deal. We'll call this our target equation. So the next challenge for us is, how do we manipulate these equations here such that we end up with this target equation? So what do? We inspect these equations here to see if any of them contains one of the species that is present in the target equation. Let's look at equation number 1. When you inspect equation number 1, you can see that carbon is on the left side here, but carbon is also present in this target equation. But this target equation has 2 moles of carbon, and this one here has only 1 mole of carbon. So the strategy is this. We will retain this equation as it is because we want carbon to be on the left side as it is in the target equation. But we need to multiply every species in this equation that's provided here by 2, such that in the end we'll have 2 carbon in front here. And that includes the energy term that's given here. Okay? Next, inspection of this equation shows that, what do we have? We have hydrogen again here, and hydrogen is present here. Again, we only have 1 mole of hydrogen here, but we have 2 moles here. What do? We keep this equation as it is, but multiply everything by 2, including the energy term. But this equation here has ethene or ethylene on the left hand side, whereas in the target equation it is on the right hand side. So this is what we do. This equation must be reversed such that this will now appear on the right hand side. Another thing to note is this. When you are reversing an equation, whatever sign is in front of the energy term must also be reversed. So this guy that's having a negative sign there will then become, so let's see what we did here. This was the first equation. That equation there, well, we multiplied everything by 2. So now we have 2 carbon, 2 oxygen, 2 carbon dioxide, and look what happens. That was the energy there. It's now doubled. Same thing we do with equation 2. That was equation 2. That's equation 2 now, when everything is doubled. Equation 3. This is now how equation 3 is written after it is reversed. This was equation 3, and that was the sign on the energy term there. And you can see now, this is how it looks like when you reverse it, and see the sign there has been changed to positive. Now what we will do is this. We will combine all of these equations here. We will combine equation number 1 with equation number 2 and with equation number 3. Bringing all of these together, we have them as shown here. So what we do now is to look for things that are common in both sides and cross them out. Carbon dioxide is here, we cross that out. 2 waters are here, water is here, and water is here, take that out. You have 3 oxygens over this side, you have 2 here and 1 here, take them out. So what you're left with are these. you're going to have 2 moles of carbon with 2 moles of hydrogen, and on this side you're going to have 1 mole of ethene alone. And when you add all of these up together, you get that amount of energy. So you can see now that the elements and compounds that are present in the equation that's produced here are exactly what we had in the target equation. So this is an example of a problem that illustrates to us how Hess's law can be used to calculate the standard enthalpy change for a reaction such as this one here that can be done using calorimetry. Another sample problem is this one here. We are having hydrogen sulfide being burnt in oxygen to give you sulfur dioxide and water, and we are required to find the standard enthalpy change for that reaction. But you're given these other reactions here whose enthalpy changes have already been determined by calorimetry. So the next job for us to do is to manipulate these equations that we've done before, such that when you add them, we'll end up with this target equation here. So again, inspect these equations here to see what species are present in them and what is present in the target equation. We can see that water is present here, and water is also present here, but this has only 1 mole of water. So what do you think we should do? We multiply everything by 2 and also multiply the energy term here by 2. Next, hydrogen sulfide is here, but is on the opposite side in the target equation. So what do you think we should do? We'll have to reverse this equation, but since we are having 2 moles over that side, then we'll have to multiply everything by 2. So reverse this one and multiply everything by 2, including the energy term. Well, we said something about the energy term. When you're reversing an equation that has an energy term with 1 sign, the sign must be changed. Right now it is positive. What do you think will happen? It should become negative. Okay? Finally, we are having sulfur dioxide on this side, and we have sulfur dioxide on the same side here, but we have 2 moles across here, but only 1 mole here. Again, we'll multiply everything by 2, including this energy term here. No changing of the sign on that. And this is how the equations have been manipulated in such ways that in the end their addition gives the target equation. So I'm going to add all of these together. So this one here is multiplied by 2. You get that amount of energy. This one is reversed and multiplied by 2. We've spoken about this energy term here. It will become negative. Let's see what it was before. Yeah, it was positive. And this one was multiplied by 2. And we ended up with that amount of energy. Our next job is to remove those elements or compounds that are common on both sides of the equation. So this one is hydrogen here, that is removed. 2 sulfur is here, 2 sulfur is here. So in the end you're going to have 2 moles of hydrogen sulfide reacting with 1 here and 1 here, 3 moles of oxygen. They give you 2 moles of sulfur dioxide here, and these 2 moles of water here. And when you add all of these together, that's your standard enthalpy change that's produced. There is a third way of calculating enthalpy changes for reactions, and this involves the use of what is called standard molar enthalpies of formation of compounds. Standard molar enthalpies of formation has this notation here. The following reaction is used to show how the standard molar enthalpy of formation of carbon dioxide can be obtained. We have this equation here where carbon is being burnt in oxygen to give you carbon dioxide, and it is happening at SATP conditions, which is 25 degrees Celsius and 100 kilopascals, and the amount of energy produced is that. This energy is called the standard molar enthalpy of formation for carbon dioxide. What does that mean? Let us unpack this concept of standard molar enthalpy of formation. So read this paragraph here. Hopefully it makes some sense. In calculating the standard molar enthalpies of formation for compounds, the individual elements from which they are formed must be in their standard states. And the elements that are making carbon dioxide, for example, are carbon and hydrogen. And these are in their standard states. Standard state means the usual states in which they're found in nature. What this is telling us is this. The carbon used in the above reaction cannot be in the form of diamond, for example, but as coal. Nor can the oxygen be in the form of a liquid, but as a gas. If liquid oxygen is used, it will entail the use of energy to change it to a gas before it could react. The enthalpy change produced will thus be less. Next point to note is this. The standard molar enthalpies of formation for elements in their standard states is 0. The standard molar enthalpies of formation for compounds have already been determined experimentally and can be obtained from a book of data. We will now show how you can use standard molar enthalpies of formation to calculate enthalpy changes for some reactions. Here we are burning methanol or methyl alcohol in oxygen to give you carbon dioxide and water. Now you have to be very attentive to the states of these species in the reaction. If I place a G here instead of a liquid and I looked up its molar enthalpy of formation, then I'll have to check it out for what it is for gas instead of liquid. And that value will be different from what is it for the liquid. Therefore, whenever you're doing these calculations, make sure that the states of these are properly represented and also accurately obtained from the book of data. You cannot go and take the standard enthalpy of formation with solid carbon dioxide and insert it in this equation, for example. This is a general equation that's used to enable us to calculate the standard enthalpy of reaction for a particular change. To do that for the one in focus, we take the sum of the enthalpies of formation for all the products and subtract from that the sum of the enthalpies of formation for all the reactants. In this reaction here, we'll take the standard enthalpy of formation for 1 mole of carbon dioxide, add that to 2 moles of standard enthalpy of formation for water vapor, and you subtract from that 1 mole of the enthalpy of formation for methanol plus the enthalpy of formation for 1.5 moles of oxygen. Using a book of data, this is what is obtained for carbon dioxide. That is what for water vapor. This is methanol, but 0 for oxygen because the standard enthalpy of formation for any element in a standard state is 0. So always remember that. So adding these together now, we end up with that amount of energy. So one more time, we're saying the third way of finding the standard enthalpy for any change is to use what is called standard molar enthalpies of formation for all the species in the chemical equation. We'll take the sum of the standard molar enthalpies of formation for all the products, and we subtract from that the standard molar enthalpies of formation, and that will give us the value for the standard enthalpy of reaction for that change. And in this case, we're burning methanol in oxygen to give you carbon dioxide and water. To do this one here, we took the standard enthalpy of formation for 1 mole of carbon dioxide, 2 moles of water vapor, added them together, and we subtracted from that 1 mole of enthalpy of formation for methanol. Oxygen is 0, and then we ended up with that value. Be attentive to this negative sign here. Right? For this part of the calculation, we ended up with that amount there, right? But because of this negative sign outside of the bracket, this negative sign had to be changed to a positive sign here. So be attentive to this negative sign here. If it was negative there, you'll end up with a positive value here. If that was positive, then it will be negative here, okay? For the reaction above, again, the enthalpy change can be represented in a number of ways. Use the thermochemical equation, and you can use the energy produced as a part of the equation as a product. Or you can use the delta H notation here. Since it's an exothermic reaction, there's going to be a negative sign here. Or you can use the enthalpy diagram here, where you're having the reactants forming products here. High potential energy, low kinetic energy molecules. And these have high kinetic energy but low potential energy. And that's the change that's taking place here. You could have extension of these types of problems. For example, they could have asked you to find out what mass of methyl alcohol must be burned to change the temperature of 5 kilograms of water from this to this temperature. First of all, you find the amount of heat produced using that. Q is equal to mc delta T. You know the mass, you know the specific gravity of water, and you know delta T. Then you find number of moles of methyl alcohol using this equation here. This becomes delta H. Number of moles will be equal to your delta H divided by the molar enthalpy of combustion, which you've calculated here using that. And then, of course, you can find its mass by using this equation here.